Hello, I'm Ziba Akarcalı, and I will be presenting you the paper named A Case Study on Common Grounds of Building Information Modeling and Lean Construction, Dudullu-Bostancı Metro Line. My co-author is Professor Dr. Esin Ergen. Building information modeling is a major technological and theoretical development for the architecture, engineering, and construction industry. Sachs et al. Defined BIM as a transformative information technology as it is the integration of parametric AEC and information management, which both took off concurrently in the late 90s. Unlike the widely utilized computer-aided design tools, BIM enables visualization of form, behavior, function, and various other information of building design and construction with its object-oriented properties. Lean construction developed itself as a new conceptual project and construction management approach in mid-90s. Essentially, lean construction is a translation rather than a direct application of Toyota production system principles, which is later labeled as lean production by Womack and Krafik. Albeit it's a translation of principles, the focus of lean construction is same with its parent concept: reduction of waste, increase the value of the customer, and continuous improvements. Recent studies show that BIM is an effective tool for addressing various principles of lean construction. Lean construction principles can be achieved and/or enhanced through BIM technologies and methodologies, which provide significant waste reduction in terms of time and material while enabling high levels of collaboration, communication, and data management. The literature review on the topic showed that there are various synergies between BIM and lean construction, and some of them are explained in detail in the following section. BIM allows reducing cycle times of a construction project by enabling rapid generation and evaluation of alternatives and solutions, clash detection, and quick performance analysis for engineering disciplines, time and cost estimation through the data which is stored in the models. A case study was conducted at a 51.560 square meter health facility with a 286 bed capacity located in Tennessee, and reducing time cycles is found to be as a major contribution of BIM to lean construction. Clash detection function of BIM found to be highly efficient for waste elimination, reduction goal of lean construction. This feature enables interdisciplinary superposition of models, detecting and correcting clashes before the implementation phase, and these may prevent waste caused by defects, weighting, overproduction, and excess processing. There were more than 600,000 clashes detected and solved before production at the site in Istanbul Grand Airport project. Encountering those clashes during execution would have cost an additional 2.5 billion euros and an extension of 10 years on the contract. Early detection and correction of those clashes provided approximately 16 million man days of time saving and approximately 850 million pounds cost saving, which is near 10% of the total budget of the phase 1 of the project. Gemba Works is an important term defined under Lean Production and Construction. Lean Construction Institute defines Gemba Works as a visual and purposeful walk at the source of the work to truly see and understand work processes and the frontline work. 3D BIM models enable the off-site employees to visit the construction site virtually, and this capability provides time efficiency for detecting and solving problems. Increase the client's comprehension of the design and construction processes of a building, providing visual coordination for the team members, which allow reducing the waste of time and effort of producing inconsistent interdisciplinary design. Throughout the literature review, the most extensive study on this particular topic was performed by Sachs et al. In this paper, the authors defined relevant lean construction principles and BIM functionalities after a literature review on empirical evidence connection, BIM and lean construction. They presented 24 lean principles and 18 BIM functionalities that are to be systematically explored in terms of interrelation. In order to complete this exploration, the authors provide a matrix in which the 18 BIM functionalities are given in the rows, and for 24 lean construction principles are listed in the columns that are that result in a total of 56 interactions enumerated and explained. 4 of these interactions are found to be negative interactions, which diminish the goals of lean principles, while the rest was found to be enhancing them. In this study, a case study on the Dudullu-Bostancı Metro Line construction project located in Istanbul, Turkey was conducted following the BIM Lean construction interaction matrix of Sachs et al. The evaluation of the matrix was performed via a set of verbal, undesigned interviews with the BIM experts and other engineers, architects of the project. Interviewees were posed detailed questions related to the relation between the 56 BIM Lean construction interactions presented in the matrix and were asked to evaluate all those relations. Also, the primary author of this particular study had worked in Dudullu-Bostancı Metro Line from January 2018 to September 2019 as a BIM and design architect in the design office. This author collated the outcomes of the interviews with her experience to evaluate the results. Dudullu-Bostancı Metro Line construction project is an ongoing underground mass rapid construction located in Istanbul. The project consists of 13 stations, 2 underground car parks, 14 kilometers of rail tunnels, a 6-story administration building, and a single-story transformer generating building. The client of the project is Istanbul Metropolitan Municipality. The consultant of the project is Tümaş Arkadis Joint Venture, and the contractor of the project is Şenbay Kolin Kalyon Dudullu-Bostancı Metro Line Joint Venture. A total of 9 interviews were conducted with the project experts. Interviewers were posed detailed questions related to the relation between 56 BIM Lean construction interactions presented in the matrix and were asked to evaluate those questions. The interviewees were asked 1 question for each interaction, 56 questions in total. 1 yes-no question for each interaction defined in the matrix were asked. The questions were asked to identify whether the interactions could be observed in the project. The answers from the interviewees were noted by the first author, and she used her personal experience for interpretation of these answers. The BIM familiarity and the lean construction knowledge level of the interviewees were given on a 3-point verbal Likert scale: 1 low, 2 medium, and 3 high. The list of the interviewees can be found below. The existence of the interaction in the project was defined based on the number of yes-no answers. If one of the answers was given by the majority of the respondents, in this case 5 or more interviewees, it was acknowledged as integrated answer of that question. Apart from these yes-no scale questions, the reasons of their answers were also discussed with the interviewees in a semi-structured way, providing insights to the authors for interpretation of the status of the BIM functionalities, lean principles, and their interactions observed in the project. The interview results showed that there were 27 out of 56 BIM lean construction interactions were observed in the investigated metro line. 25 of the observed interactions were found to be positive, meaning that the BIM utilization contributes to lean construction assertively. The comparison of each BIM functionality in terms of the contribution to lean principles show that multiple user viewing of merged or separate multidiscipline models is the most effective BIM functionality observed in the Dudullu-Bostancı Metro Line that enabled the most of the lean principles identified in the project with 7 BIM lean construction interactions. This functionality is followed by 1 aesthetic and functional evaluation, which enables 5 lean principles to be observed in the project. The rest of the functionalities present a maximum of 3 positive interactions with lean principles. The positive interactions suggest that the project was successful at performing all of the BIM functionalities except for the 3rd functionality, which is the predictive analysis of performance, and the 17th functionality, which is the integration with supply chain database. The 17 BIM functionalities identified in the project were found to be enabling 22 out of the 24 lean construction principles given in the matrix, except for reducing the changeover times and cultivating an extended network of partners. Even though the majority of the BIM functionalities and the lean principles given in the article were detected in the project, less than half of the 56 interactions were identified by Sachs et al. Were observed. These findings show that performing all BIM functionalities did not automatically ensure the delivery of all aforementioned lean construction principles. The interviewees agreed that the project could have shown more positive interactions if the BIM utilization were more advanced and less compromised because of the traditional construction project management methods that were used. Also, even though the BIM familiarities of the most of the interviewees are at the medium level, BIM knowledge of the interviewees found to be low, except for the interviewee number 1, creating an obstacle for utilization of BIM at its possible maximum potential. The minimum application level of the BIM knowledge of the contract parties may explain the missing interactions on the matrix. The 29th and the 41st interactions were found to have negative impact on the BIM lean construction interaction that highlight the drawbacks of BIM utilization on lean construction. These interactions were observed at the 11th, 12th, and the 13th BIM functionalities, which are related to the rapid design alternative generation and BIM evaluation. The 11th BIM functionality, automated generation of construction tasks, appeared to be only negatively contributed to the lean properties in the Dudullu-Bostancı Metro Line. In this context, it can be argued that establishing a wide inventory of detailed design alternatives may cause delaying the necessary selections while causing management complexity, leading to time and inventory wastes. The experts in the Dudullu-Bostancı Metro Line agreed that the observed BIM functionalities are not practiced at its full potential. For example, the 5th BIM functionality, the evaluation of conformance to program client value, was not utilized in all aspects of the project, thus only providing interaction with lean construction principles A partially, and C, while missing the interaction with principles A partially, B, R, S, T, and U. On the other hand, utilization of BIM does not always mean abandoning traditional construction methods, which usually oppose lean construction principles. In this project, the project management was conducted by using traditional methods rather than using BIM processes described in the standards, showing that BIM was not utilized at its full potential. Here we can see the adapted interaction matrix from Sachs et al. For our case study. This is the interview results table. Conclusions. In order to investigate the relation of BIM with lean construction, a case study was conducted by using BIM lean interaction matrix developed by Sachs et al. The Dudullu-Bostancı Metro Line construction project located in Istanbul was chosen as the case study project. A total of 9 structure interviews were conducted with the architects and engineers of the project, questioning the existence of any BIM lean construction interactions. The results of the interview showed that 22 of the lean principles were achieved by utilization of BIM and 16 BIM functionalities were observed in the project. Even though the majority of the BIM functionalities were observed, it was found that utilization of BIM does not enable the practice of all lean principles, since only 27 of the 56 interactions were identified in the project. The findings show that BIM was not utilized in the Dudullu-Bostancı Metro Line at its full potential. This low performance of BIM resulted in losing the chance of practicing more lean principles and less waste through BIM application. It is agreed that the traditional construction management methods utilized in the project hindered the adoption of BIM at its full potential, since these traditional methods oppose lean construction. This resulted in a lower number of lean principles observed in the interaction matrix. It can be argued that in order to observe more lean construction principles in the project, the quality of BIM functionalities should be improved first. On the other hand, apart from the BIM familiarity and knowledge, lean construction knowledge and the lean potential of BIM should be endorsed and acknowledged. In order to achieve more lean principles through BIM utilization, the properties of BIM that can serve to the lean construction should be deliberatively considered and applied to the project. In brief, it is a start to utilize BIM for linear construction projects, but it's not possible to achieve a true lean project that operates with BIM without knowing and endorsing the lean properties of BIM, and more so over setting lean construction as a management strategy. Even though it's known that the project could not utilize BIM at its full potential because of lack of knowledge, opportunity, and commitment caused by traditional mentality, it was observed that the project still showed lean properties through the BIM functionalities without the aim of following lean construction principles. These results show that BIM could be an assertive partner of lean construction, and it can be acknowledged that there is indeed an unintentional synergy between BIM and lean construction. There are several other metro lines in Istanbul, Turkey, that utilize BIM, and this study may be extended by the inclusion of these particular metro lines for a better understanding of the relationship between BIM and lean construction, and to identify the flaws that prevent the interactions between. We would like to thank Istanbul Metropolitan Municipality for providing an official permission for the utilization of the project data in interviews with the project experts. We would also like to thank the interviewees from Istanbul Metropolitan Municipality Directorate of Anatolian Side Rail Systems, Şembel Kolin Kalyon Dudullu-Bostancı Metro Construction Joint Venture, and Arkadis Tumaş Joint Venture. Thank you.